Okay. Good morning, students. In today's session, we'll discuss about the one of the transformation techniques for the IIR filter design, bilinear transformation. So already we have discussed the impulse invariant method, the two transformation techniques to convert your analog into digital filters. So in the bilinear transformation, okay, so the transformation technique by linear transformation. Bilinear transformation, because for IIR filter, this is actually IIR filter design techniques, IIR filter design techniques. Okay, so already we discussed about the impulse invariant method. The other one is a bilinear transformation, BLT method. It's a bilinear transformation. So bilinear, from the name itself we can say, so the two transformations from S domain to R domain and R domain to Z domain. Okay, so how in the bilinear transformations, what are the frequencies in analog domain? So the analog frequency domain, the frequency range is minus infinity to plus infinity. Okay, plus infinity. So this compressed into digital domain by using the bilinear transformation. It is a digital frequency domain, is a omega. Okay, the range from compressed into minus pi to plus pi, less than or equal to, than equal to. Okay, plus pi. So this analog frequency is compressed into digital frequency. So the range from minus infinity to plus infinity to the compressed ratio between minus pi to plus pi. So this is omega is analog frequency, and this omega is digital frequency. Digital frequency to the sampled frequency, the sampled frequency, you know, the desired sample frequency, which is equal to pi by t. So pi by t, or you can say, which is equal to omega s by 2. So what is the sampling frequency? 2 pi by t. So 2 pi by t. This is a desired frequency. So it is a straightforward method. Okay, the bilinear transmission technique. So compresses the entire analog frequency range to the digital frequency range. That is a, you can say, you can say this on 0 to fs by 2. So it is a straightforward method, a stable transformation to the stable, that is a, by converting is a straightforward method from analog to digital h of z. Okay, so here how it is transformed, how the S plane. So this is your S plane. What are the points? How you are going to mapping all the points in the left half of the S plane. This is the left half of the S plane. Okay, so this is the left half of the S plane. So this is J omega and this sigma plus J omega. So this is the right half of the S plane. So this all the points, how we are mapping these, all the points on the in the left half of the S plane mapped to the inside the unit circle. So this imaginary axis is mapped to unit circle. This is the imaginary axis. In the Z plane, it is the imaginary axis. So it's a unit circle. Unit circle. So this is your Z plane. is omega equal to 0, this is omega is equal to infinity. This is a unit circle. Okay, so how the points in the left half of the S-plane mapped into the unit circle, that is a inside the unit circle, inside the unit circle. And all the points on the in the right half of the S-plane will be mapped to the outside the unit circle, outside the unit circle. Okay, so this is mapped to the outside the unit circle, and the left half of the S-plane points are mapped into the inside the unit circle. So now we'll see the already we derived the uh, okay impulse invariant method. What is the relationship between analog frequency and digital frequency? The relationship between analog frequency and the digital frequency. Okay, for impulse invariant method and bilinear transformation method. If you see, this is the digital frequency, this is analog frequency. So this is omega t, this is our digital frequency omega. Okay, so this pi, for example, this is range min pi, this is pi by 2, this is minus pi by 2, this is minus pi. So this range. Okay, so if you see the frequency, the analog and digital frequency, so this is equal to impulse invariant. For impulse invariant, what we have derived, omega is equal to omega t. Omega is equal to omega t. Okay, so mathematically, due to the tangential function, this is your omega. What is the omega? We'll discuss. For this omega, just 2 tan inverse omega t by 2. So this is your relationship between analog frequency and digital frequency for bilinear transformation. So we'll discuss how we derive this one. So the entire range of omega analog frequency, the range. Okay, so if you want to draw the full waveform, you can draw this minus pi to plus pi. Okay, so this is 5, for example, this is 5, 10, this is minus 5, minus 10. So mapping between the frequency variables omega and this omega. Okay, for Bilinear transformation. This is for impulse invariant. So due to the tangential function, the arc tangent, this is a arc tangent function. Arc tangent function. Due to this arc tangent function, this omega and this omega are non-linear function. Non-linear function. Due to this non-linearity, there is a frequency warping. It's called frequency warping. Frequency warping means frequency distortion. Warping means distortion. Distortion. So due to the non-linearity function, we'll derive now. Due to the non-linearity function between omega and omega, this is called, there is a distortion will be there. So this is called frequency warping. So that we have to do pre-warping first. Pre-warping, here the technical term, pre-warping. What do you mean by pre-warping? Converting your analog to digital. So pre-warping, convert your analog into digital frequency, into digital frequency. This is a pre-warping. Okay. So if you see that, so no need to derive the complete derivation. You can refer the Procchia's book, the bilinear transformation. There are two transformations, as I said, from S plane to R plane and R plane to Z plane. Okay, if you consider the first order case, for example, the h of s is equal to b divided by s plus a. This is a first order system. So if you take h of z for this one, you will get b divided by s is equal to 2 by t. Okay, 1 minus z inverse by 1 plus z inverse in plus a. So where s is equal to, this is s. So you can write 2 by t z minus 1 by z plus 1 also. Or you can write 2 by t, this is 2 by t 1 minus z inverse by 1 plus z inverse s is equal to. So this derivation how you derive now, you can refer the book. So this is a s and s domain to this is s domain to direct transformation to z domain. So if you see the mapping for the bilinear transformation is only one-to-one mapping. You can say it's a one-to-one mapping. Okay, so this is a one-to-one mapping. Bilinear transformation is one-to-one mapping because the impulse invariant method is many-to-one mapping. Already we discussed many-to-one mapping. Here one-to-one mapping only once. So this is the imaginary axis. If you see the unit circle, this is your imaginary axis, unit circle. The imaginary axis is transformed into the unit circle only once. Okay. Okay. So now the relationship between analog and digital frequency for bilinear bilinear transformation method. So let us take what is S is equal to. You know that S is equal to S domain analog frequency S equal to J omega. Okay, so the J omega points on the imaginary axis will be mapped to the Z plane on unit circle. That is Z equal to e power j omega. So this analog frequency imaginary axis is mapped into the unit circle of the Z plane at Z equal to e power j omega. So what is S actually? So S is equal to 2 by T and 1 minus Z inverse by 1 plus Z inverse. So put S is equal to j omega. So put S is equal to j omega, which is equal to, and put Z equal to e power j omega. So 2 by T. Okay. So 1 minus e power z inverse e power minus j omega by 1 plus, that is e power minus j omega. Okay, so you know that the trigonometry functions e power j theta into e power minus j theta is equal to 1. So now you can write 2 by t. So 1 can be written as e power j omega. Okay, so another function, you know, sine theta is equal to e power j theta minus e power minus j theta by 2j. Similarly, cos theta is equal to e power j theta plus e power minus j theta by 2 by 2. Okay, so now, so here e power, you can write the 1 can be written as e power minus j omega by 2. 1 can be written as e power j omega by 2 into e power minus j omega by 2. 1 can be written as this one. This one can be written as e power j theta e power j omega by 2 into e power minus j omega by 2. So minus e power minus j omega, this one. Okay, this one e power minus j omega. So this one can be divided by, similarly, e power 1 can be written as e power j omega by 2 into e power minus j omega by 2. It will be 1 plus, so e power j omega by 2 into e power minus j omega equal to 1 plus e power minus j omega. Okay, so it is equal to, you can write 2 by t, so this is j omega. Okay, so this term, so you take e power minus j omega by 2 common term. So then inside e power j omega by 2 into e power minus j omega 2 minus e power minus j omega by 2. So this will be e power j omega and e power minus 1 minus, it will be cancelled, 2 will be cancelled, so only j omega will be there. So divided by, again you can take the common term e power minus j omega by 2. So e power j omega by 2 e power j omega by 2 plus e power minus j omega by 2, this one. So now can be simplified again, 2 by t. So this will be sin omega by 2 and cos omega by 2. So 2j, so you substitute the trigonometric formulas, finally you get sin omega by 2 divided by cos omega by 2. Okay, so the omega, this is j term will be cancelled, so 2j, so we'll get 2j here, 2j sin omega t, jj will be cancelled. So this j omega and 2j, 2 by t. So this into here, if you substitute the formula, here 2j, here 2. So this j and j will be cancelled, this 2 will be cancelled. So we'll get only 2 by t tan omega by 2. So omega is equal to 2 by t tan omega by 2, or you can write analog frequency, or omega is equal to analog frequency 2 by t, this is analog frequency 2 by t tan omega by 2. Okay, so omega by 2 is equal to, omega by 2 is equal to tan inverse. Okay, tan inverse omega t by 2, omega t by 2, omega by 2 is equal to tan inverse of omega t by 2, omega t by 2. So now omega is equal to 2 tan inverse omega t by 2. So this also you can highlight. So this is a relationship between analog and digital frequency. So due to the tangential function, now you can see, so now you can map, so this, okay, you can map that. So this range, so this is omega, this is analog frequency omega t, so pi, okay, this is pi by 2 minus pi, this is minus pi. the tangential function. This omega is equal to 2 tan inverse omega t by 2. So the entire frequency range is mapped into, okay, minus pi to plus pi. So the unlock frequency range from in minus infinity to plus infinity is compressed into minus pi to plus pi. So this is pi by 2, this is pi by 2, this is minus pi by 2. So the range, so here for example 5, 10, this is minus 5, minus 10. So this is a mapping between the frequency variables, this omega and this analog omega. Okay, so remember that how to, what is the S relationship between the, how the S mapped into Z domain, and what is the relationship between analog frequency and digital frequency, how the analog frequency minus 50 plus 70 is compressed into the digital frequency. So due to the tangential function, the arc tangent function, this omega and this omega is non-linear. So because of non-linearity, there is a frequency warping. Frequency warping has nothing but frequency distortion. So you have to do the first step, pre-warping. Okay, so pre-warping, this is called pre-warping. Pre-warping means due to the nonlinearity functions of omega and omega, frequency distortion will be there. Frequency warping and frequency distortion will be there. So we are converting analog to digital. This is called pre-warping. Okay. So like impulse invariant method, we'll take some examples and we'll solve the transformation techniques, conversion from analog filter into digital filter by using bilinear transformation. So bilinear transformation method. So for example, the analog transfer function is given h of s, which is equal to 2 by s squared plus 3s plus 2. So you have to determine the h of z by using bilinear transformation. So you take the two cases where the t is equal to 0.1 second or the t may be given 0.5 second. Okay. So what is the given 3s? So wherever s is, what is bilinear transformation? Put s is equal to 2 by t 1 minus z inverse by 1 plus z inverse. So which is equal to, so h of z is equal to, so the function 2 divided by s plus s squared. So s squared means 2 by t 1 minus z inverse by 1 plus z inverse s squared plus 3 into s. 3 into s is 3 into 2 by t 1 minus z inverse by 1 plus z inverse plus 2. So a plus b into a minus b. So you can substitute 2 by 2 squared will be 4 by t squared, 4 by t squared, 1 minus z inverse squared divided by 1 plus z inverse squared plus 3 2s are 6 by t into 1 minus z inverse divided by 1 plus z inverse plus 2. So simplify, is equal to numerator term 2 divided by, okay, so 4 by 4 in the common term will be this one. So 1 plus t square into this one, t squared into 1 plus z inverse square, we can take common term. So the numerator term will be 2 into, okay, so 2 by, so this is normal 2 by, this is 2 by, this is 2 by numerator. So here this term will be 4 into 1 minus z inverse squared, this numerator term, plus 6t, 6 into t Okay, 1 minus z inverse plus 2t squared 1 plus z inverse squared. Simplify. So you can simplify again. The numerator term becomes, this will become to numerator term 2 into t squared of 1 plus z inverse the whole square divided by the denominator terms are 4 into 1 minus z inverse squared plus 6t into 1 minus z inverse plus 2t squared into 1 plus z inverse the whole square. Now you apply t is equal to 1 first case. So when you apply t is equal to 1, you will get 2 into 1 plus z inverse square divided by 4 into 1 minus z inverse square plus 6 into 1 minus z inverse plus 2 into 1 plus z inverse square. So you apply the formulas, trigonometric formulas, the a plus, yeah, a plus b the whole square and a minus b the whole square. Apply the formula a plus b the whole square and a minus b the whole square. A square plus b square plus 2ab, a square plus b square minus 2ab. So you substitute. So finally you will get, so 2a plus b the whole square, a square plus b square plus 2ab. So 2 into a square plus b square plus 2ab. 2ab 2 z inverse plus b square z minus 2 z minus 2 z minus 2 numerator term will be. Similarly 4 into a minus b the whole square, so a square minus 2ab plus b square and plus 6 into 1 a minus a square minus b square, so 6 into 1 minus a square minus b square is z minus 2 and plus 2 into a plus b the whole square, so again 1 plus 2 z inverse plus z minus 2 this term. So now you can simplify, multiply 2 plus 4 z inverse plus 2 z minus 2 numerator term, okay, divided by 4 6 plus 4 10 plus 2 6 plus 4 10 plus 2 12 minus z inverse 8 8 minus 6, here 4, this is 4, this is 4, this is minus 6, minus 6 there and 1. Okay, you will get z inverse 12 minus 4 z inverse. Simplify the terms. So again you will get here 2 plus 4 z inverse plus 2 z minus 2 divided by 12 and take it outside, 1 minus 4 by 12 z inverse. So again you can simplify. So this is 2 by 12 plus 4 by 12 z inverse plus 2 by 12 z minus 2 divided by 1 minus 4 by 12 z inverse. So now you can simplify 2 by 12, the coefficients can be written as, so 0.1667, 4 by 12 0.333 z inverse plus 2 by 12 plus 0.16667 z minus 2 divided by 1 minus 4 by 12 0.333 z inverse. So these are the coefficients. Similarly, you apply t is equal to zero point 0.5 or 0.1. What is the problem is given? 0.1 second. Point point t is equal to 1. The second case 0.5. So 0.5 seconds you can apply. Okay. So this is the bilinear transformation techniques. Similarly, some of the problems I'll give it to you. You can practice. So you can take the problems from the brochures. Brochures are opening. So some other examples I'll give it to you. So H of S problems. H of S is equal to 2 by S plus 1 into S plus 2, where take t is equal to 1 second. Okay. Similarly, this is the first one. Second one, H of S is equal to S cube by S plus 1 into S square plus S plus 1. Here also take t equal to 1. So wherever S is there, put S is equal to, you know that S is equal to 2 by t, Z minus 1 by Z plus 1. Or you can say 1 minus Z inverse by 1 plus Z inverse. 1 minus Z inverse by 2 by t into. So the problem H of S is equal to 2S divided by S square plus 0.2S plus 1, and you take t equal to 1. S 2S divided by S square plus 1 S cube. Okay, so these problems you can practice, and some more problems you can take from the book exercise problems and practice. And one more problem, the fourth one, H of S is equal to S plus 0.3 divided by S plus 0.3 the whole square plus 16. Take t is equal to 0.5. So this problem take t is equal to 0.5. If t is not given, you take t as a 1. So you can then apply the partial fraction methods. Okay. So I think I will conclude this session. So in IIR filter design, for conversion of analog to digital filter, there are two transformation techniques: bilinear transformation technique and impulse invariant method technique. So with the concept of the relationship between the analog and digital frequency, and what is the relationship between the tangential function of bilinear transformation, you can practice with some more problems. Yeah, thank you. With this we can conclude. Thank you.